Though, in talking about the inclined plane, I did bring up what the simple machines were, right? We were able to list those all out. Good, because I like talking about simple machines later in the year, but not right now. So let's, it's important to me that you understand that the inclined plane is like the go-to thing for every teacher who wants to make kids cringe. And I've never understood really why, because once you've done one inclined plane problem, you've probably done them all. But when it comes to the AP exam, they lean into the inclined plane like way heavy. And every single teacher who teaches physics is going to put an inclined plane problem on their test. Every one of them. So since I fall into that category, you should probably expect me to do the same. More importantly, and more to the point, inclined plane problems allow us to explore three things about you that you might not be aware of. The first, it allows us to understand if you get the interplay between the forces, apart from the fact that there are 5 or so that we have to worry about. That changing this angle doesn't change just one thing, but it changes lots of things all at the same time. And if you don't believe me, then here's what I'd like you to do. I would like you to come up with an expression for the acceleration of object M on a ramp of angle theta, where the surface is frictionless. You did a problem like this, but I'd like you to come up with an expression. So I'm going to stop for a moment, let you work. You should be able to go back through your notes. And my expectation here is that in 120 seconds, you'll have a free body diagram correctly coordinated with a set of relationships that either equals 0 or MA or neither or both. I don't know. You work it out for me. Okay, in the interest of time, I'm going to draw arrows. How many arrows am I drawing? Just hold up a number of fingers so I know whether you're really paying attention or not. All right, that's good. So I think we could probably all be in agreement then. This way? Does that work out for one of them? Like downwards? And label that sucker weight or mg. On the AP exam and on my tests, whether you label it weight or mg is fine. So if you decide to label it mg, good. I would encourage you to label it weight, but you won't be marked off if you label the weight mg instead. Unless, of course, you're required to label it weight. I'm saying this because your problem will dictate the values that can be in your answer if they ask for an expression. So if your expression has to have weight in it, then you can't substitute mg. But if your expression has to have m and fundamental constants in it, then you might want to just cut to the chase part and get that in there as soon as possible. The next force, you have no choice. And I've been watching students a lot in AP Physics 1 screw this up, but I don't want to see that here. I want to say it once, because we're in mechanics and higher level thinking and all that, and note that all of you know that this has to be perpendicular to the surface in contact, period. You don't get a choice. So it's perpendicular to the surface in contact. That looks kind of perpendicular to me. Probably not perfectly perpendicular, maybe more like that. So then I grab that, put it right over there. That has to be the normal force. Now, here's the deal. Those are the only two forces that act in a system. And looking at those two forces, they should tell me the direction that the system accelerates. But you know the direction the system accelerates. The object is unlikely to accelerate this way, as much as you might want it to. It's constrained to move in a particular direction. I'm saying this because it's important you understand the normal force, and this is for your notes, and this has not been said before. The normal force is what's called a reactive force. It reacts to the circumstances that are presented. It can grow, it can shrink. As long as the incline doesn't break, the normal force can be whatever value is necessary to prevent the object from going through the surface. But it can also go to 0 if it's unnecessary. You're going to see that in just a minute. So be aware that the normal force is reactive. It is a part of the circumstance of the problem. In this case, the normal force is preventing the block from sinking into the ramp, which is constraining the motion of the problem this way. The block can only slide down the ramp in this direction. So under these forces, it seems not unreasonable to set my coordinate system in the direction of the likely acceleration, which is down the ramp. Now, this brings up something important to me. This has become our x direction. So how big I drew the normal force isn't related directly to the weight. It's related to this much of the weight. Because my y-axis is going to be aligned with the normal force. And therefore, when I draw this free body diagram, I'm attempting to demonstrate balance. And the balance I'm trying to demonstrate isn't in the x direction. The balance I'm trying to demonstrate is in the y direction. It should be balanced in the direction related to the ramp, because the object is not accelerating into the ramp, but down the ramp. So the normal force's length does matter and shouldn't be arbitrarily drawn. Now, the AP exam is not going to be super critical of that, but the next part of this has to do with this angle. Many students don't know whether theta goes here or theta goes here. Now it should be easy to kind of determine because I made the angle small on purpose. But one way to help you with this is to realize that we tended to start our axis aligned with the horizontal. And then we tipped the x-axis to align with the ramp. Does that make sense? So with that knowledge, the horizontal was somewhere like here. So we turned the x-axis theta degrees to be aligned with the ramp. That had to force the y-axis to break from the weight and turn this direction the same number of degrees. That's how you can figure out where to put the theta, is to remember that we tended to start horizontal and then turned to be on the incline. So y would have lined up with the weight, but you turned it away from the weight to line up with the incline. It's not a hard and fast rule, but it should help you guys, especially when the angle is not obvious. Or more importantly, maybe with the next one where the angle can change. So that's a good start. That gets us our coordinate system. From this point forward, I'm of a mind that I don't have to help you any longer. Meaning, these are the things that are new. The rest of this, you've been doing. You've been taking a vector and breaking it up into its components. You've been adding up components that are in the x direction and components that are in the y direction. This is the part that we've been practicing for the last 6 weeks total. So I don't think there's any issue with you guys setting up a triangle, wrapping it around the angle. Recognizing that this one has to be the weight times the cosine of theta, because it's on the adjacent side. And this one is the weight times the sine of theta. This is the part we've been practicing. Just because the coordinate system isn't perfectly upright doesn't change the fact that you've been breaking up vectors into their components. So I didn't put all that practice out there to now have to reteach this part again. But I do want you to recognize that this is a Newton's second law problem. And here's where I'm going to be ultra critical. We changed the coordinate system to line up with the acceleration as our number one priority. Right, that's what I said. You have two priorities for setting your coordinate system. The first priority is to line it up with the acceleration. The second priority is to line it up with as many forces as possible. Now that means that even if you can't line it up with many forces, you line up with the acceleration first. no matter how many forces have to be resolved afterwards. And the reason that's important is when you break this up into the net force in the x direction and net force in the y direction, you would like one of these to be 0. If not, you're hosed. Your problem becomes infinitely more difficult if you can't do that. So you want to make sure that you set this up so that one of them is the direction of the acceleration, one of them isn't. We won't always get that opportunity. Sometimes we're just going to have to suck it up and have 2 different accelerations. But at this moment, we don't. We can do it this way, taking it easy. So once I've kind of identified that, I just obey the rules here. Add up all the forces in the x direction, set them equal to ma. Add up all the forces in the y direction, set them equal to 0. So weight sine theta equals ma. Normal minus weight cosine theta equals 0. Now, I'm going to say this to the people who are novices here. The people who had physics before have a singular advantage over you, and that is experience. You want to catch up to them faster? Look into the future and notice that no matter what, if there's an object on an incline, those are always going to be the components in the x and y direction. It will always be true. Because no matter how I draw an incline, if the angle is always compared to horizontal, those are always the 2 components. Always. It might be in your best interest to make a quick note of that, which is what I would have told the mechanics, the AP1 students next week when we do theirs like this. Because the inclined plane shows up on a multiple choice, which means 1 minute and 13 seconds. Do you really want to draw a free body diagram during the multiple choice? You don't. You want to commit this to memory. The kids who had AP1 last year, they already have. That's their advantage. We're largely done now. I wanted an expression for the acceleration, and that expression is here. So I plug in mg, and I say mg sine theta equals ma. And here's where normally we would just cancel these out, and we will get that the acceleration equals g sine theta. And you could go one step further and say the normal force is going to be mg cosine theta. That happens a lot too. That's very, very common for inclined plane problems. And it's worth recognizing that as the angle gets bigger, the normal force gets smaller. And as the angle gets bigger, the acceleration gets bigger. Cosine gets smaller as the angle gets bigger, and sine gets bigger as the angle gets bigger. Things to keep in mind. That's why if you keep tipping something upwards, something will eventually begin to move. Even if you have to make it 90 degrees so it just falls off, it's going to eventually move. Here's the thing. Because I like you guys to be more intellectual than intelligent, I do like that better, and because I think intelligence has value, it's at this moment where it'd be nice to at least have an intellectual conversation. This side comes from Newton's second law, which means this is inertia. It's how difficult it is to move the object. This side comes from something we haven't studied yet, the gravitational force of attraction between objects with mass. We haven't studied that yet. We will, but I need to have a moment where I remind you that there's gravitational mass and inertial mass. And although they are measured to be the same, they mean different things. And I can't tell you why the universe works this way. I can't tell you why gravitational mass and inertial mass do the same thing, meaning have the same measurement. Proving that they have the same measurement took about 150 years. It's now been proven, but it should be interesting to note that this part is how an object responds to force. It's not like it has sentience, but this is an object's resistance to a force. It's why it doesn't want to move or want to change. This is a blind obedience to the force of attraction between masses. So the reason why mass cancels out here and does a lot in physics is because of this relationship that they're the same. We're going to find that mass cancels out a ton. All you people that are doing this for the second time, how many times does the mass cancel out? Like all the time, isn't it? Almost every single conservation of energy question, mass is going to cancel out. Momentum questions, mass cancels out. It's amazing how much the mass cancels out. And it's just because of this, which makes so many things reliant on other factors. The acceleration here has no bearing on how much mass I put there. So no matter what's on the ramp, they all accelerate the same. So you will be asked questions to rate why making something bigger or smaller may or may not make a difference. These are the moments where you need to have something to say. And being able to say, well, the mass cancels out, that might not be enough. But being able to say that the gravitational mass and inertial mass are the same, therefore we can divide them out, says more about what you know. All right, enough of all that. I want to get back to solving these kind of ridiculous problems. Any question about this inclined plane problem? We've studied it thoroughly now, because now we're going to step it up. We're going to do a different problem real quick, and I'm going to demonstrate this problem first. So, name a force. I would encourage us just to start at the top of the list and just evaluate. There's only 5 questions to ask. Ask those 5. So, gravity is not really even a question, is it? If it's near the surface of the Earth or some planet, there's going to be a gravitational force, which means we very seldom get away from that. Going to the next one on the list, is the object in contact with any surface? Yes. So I have to draw a force based on the rules of normal force. The rules of normal force is that the force can only be perpendicular to the surface in contact. This force must be drawn upwards because the surface is the floor. There are quite a few people who don't have one of those. But you should notice, I did not draw it the same length as the weight. And you shouldn't have either. I don't know how much to reduce it. But I do know that I am pulling on the object to the side and upwards at the same moment. The normal force is a reactive force. Can you imagine I could probably pull hard enough on the string to lift the chair? Well, maybe not me, but somebody who works out more than me. So maybe one of you could pull hard enough on the string to lift the chair. So I know that pulling upwards in any small way must be reducing the contact between the chair and the floor. Should I pull upwards hard enough, I should be able to bring that normal force to 0. I'm saying all that to remind you the normal force is reactive. It will react to what I am doing with the tension. I can change the angle of the tension or the size of the tension or both to create the condition where the normal force is reduced to 0. The normal force is reacting to what I'm doing. So I'm going to draw the tension, and I'm trying to keep a clear, idea of how to draw the tension so that this portion of the tension and this normal force add up together to give me the weight. Trying to keep an eye towards that. I don't have a coordinate system in place, so I'm kind of in my mind's eye imagining that the coordinate system, before I rotate it, is horizontal. And I don't know that this is the coordinate system I'm going to use, but it doesn't matter. Balance still has to be struck. So I'm checking the balance. By the way, the coordinate system doesn't create balance. The coordinate system just helps us find the balance. But I have another force to draw, I think. And I think most of you understand that I do have another force to draw, because if I didn't, this system would not have balance. It is not balanced left to right. So I'm thinking I need a force that's going to balance the fact that this is going to the right. This is another one that many people forgot, or some people forgot. But I go down my list, we're talking about friction here, right? Is one surface attempting to slide past another? Yes, so I need to draw a frictional force. The frictional force has to oppose the motion. This is not arbitrary. The surface can be left or right. But the frictional force isn't going to try and make the chair go faster. So I think we can all agree that the frictional force has to be in this direction. It has to attempt to oppose the motion of the chair. Moreover, it should be clear that the length of this vector and the length of this vector are the same. The sideways portions is what I'm talking about. I am imagining right now a line drawn this way. I'm trying to make sure the amount I have to the left is the same as the amount I have to the right. I think I've drawn my friction a little too long, but not terribly so. And we've reached kind of the end of this now. And since the chair isn't accelerating, I think this is a perfectly reasonable coordinate system. It aligns with 3 of the 4 forces. Now, the coordinate system is not necessary for a free body diagram. I've tried to say that a couple times. I want to remind you, the coordinate system is not necessary for the free body diagram. Here's what I would like you to do. The tension is T, and the angle is theta. Please come up with expressions for the normal force. And in your expression, I would like mg to be used for weight. And that's about it. So you can have T, theta, F, nope, not F, T, theta, M, or G in your answer. But I would like an expression for the normal force and an expression for the friction. Okay? Everybody understand what I'm asking you to do? I want expressions here, and you're limited to these letters only in your answer. Only one of the forces has to be broken up, correct? The bell rings, and so I want to make sure we've at least seen the answer here. Any question about that? I took the one off-axis force, applied trig to it to get my components. Cosine along the adjacent side, sine on the opposite side.
Today we are on yellow club schedule. So teachers, at this time you may release only those students with yellow club cards or specifically handwritten completed passes, and fully completely written passes for students to leave your class at this time. If you're a substitute teacher, those are the only 2 pieces of documentation you're allowed to accept. Word of mouth or a student saying that a teacher needs to see them, that's simply just not enough to release a student from a class. Yellow club cards and handwritten fully completed passes, please. Students have those in hand in the hallways right now, so administration.
So, in wrapping up, net force in the x direction 0, 2 forces. Net force in the y direction equals 0, 3 forces. Everybody good there? So our answer would be to say friction is T cos theta. Our normal is mg minus T sine theta. These are the expressions for our answers. Okay, that's probably all we're going to have for today, so I appreciate your time.